Hello and welcome to LuckyMath. In my last video I introduced you to these new objects called matrices, and in this video I want to show you a new operation, which is the matrix multiplication. Let's say we have two matrices as follows. First matrix times the second matrix gives us a third matrix, which is the resulting matrix. Now, normally when you multiply two objects, you could have some dot in between or a cross. But if you have a matrix multiplication, then really there is no sign in between these matrices. So let's first do some dimensional analysis when it comes to matrix multiplication, because if you know the dimensions of your first two matrices, then you're also gonna know the dimension of your resulting matrix. Let's assume that the first matrix is an R n cross m matrix. This means that the matrix only has real entries and it has n rows. So the first number or dimension up here stands for the number of rows of the matrix, and the second number m would stand for the number of columns of the matrix. And let's assume that our second matrix as well only has real entries, which isn't really important for what we look at, and it has dimensions m cross l. So in this case, first number stands for the number of rows of the matrix and the second number for the number of columns of the matrix. And from these dimensions, we can figure out what the dimension of the resulting matrix needs to look like. Now, probably you figured out or you saw that I chose the same dimension for the number of columns of the first matrix as for the number of rows for the second matrix. And you have to choose these dimensions the same, because if you don't, it is not possible to multiply the matrices. So this is a condition that is needed in order to get a resulting matrix. And the resulting matrix is gonna be of dimension R n cross L. Why? All you have to do is you cross this m and this m. Basically the numbers which have to be the same in both matrices. And you are left simply with this n and the l. So basically the outer numbers, and you cross away the inner numbers, inner dimensions. You're gonna see it in some more examples in a minute. So we have n and l as the dimensions of our resulting matrix, which means that we have n rows and l columns. Now let's look at some concrete example which would be a valid example for matrix multiplication, or let's check if it is valid. Suppose we have the matrix 1, 2, 3. 0, 1, 0, 1, 2, 2, and we multiply this matrix by the matrix 1, 1, 2, 1, 0, 2. Then let's first look if this is a valid matrix multiplication by doing a dimensional analysis. So suppose, or not suppose, let's count. We have 3 rows in this case and 3 columns. So this is an R 3 cross 3 matrix. So it is a square matrix, which is a nice matrix. And this second matrix has 3 rows as well, but only 2 columns. So this would be an R 3 cross 2 matrix. So if we multiply these two matrices, what we would get is an R 3 cross 2 matrix. Why? What you do again is you cross away these 3's in the middle, so the numbers which have to be the same in order to do matrix multiplication. So I really chose this number and this number to be the same as up here in order that this is a valid matrix multiplication. And we are simply left again with this 3 for the dimension of the number of rows of the resulting matrix, and the number 2, which stands for the number of columns of the resulting matrix. So the resulting matrix is gonna look somewhat like this, with 3 rows and 2 columns. And our job is now to find what numbers are in this matrix. So that's the next task that we're gonna try. And I would like to introduce this subject by looking at an operation which you already know, namely the scalar product, right? You have heard of the scalar product or the dot product, where we have 2 vectors. So for example, the vectors A, B, C times A, B, C, D, E, F. And I'm sure that you know that if you multiply these 2 objects by this scalar product, then what you do is you multiply these entries of the vectors dependent on their height. So you have A times D plus B times E plus C times F as a result. Let's write that down. So we have AD plus BE plus CF. This is what is known as the scalar product of 2 vectors. So from 2 vectors you would get a scalar. That's why it's called scalar product. Or dot product, because you write a dot in between. You really have to do that. So now the important or the interesting part is that you could as well also write this operation down as a matrix multiplication. So what you see here, this is exactly the same as writing down A, B, C matrix multiplied by D, E, F. So the only difference is there is no dot in between, so you don't so this is not a dot product but a matrix product, no sign in between. And you write this standing vector, instead that it is standing, you turn it to a lying vector. And this represents exactly the same operation as up here. So we get the same result, which is AD. So you multiply these 2 numbers and then plus these 2 numbers, B and E, plus C and F. So what we get is again exactly the same, plus BE plus CF, which is very nice, because now what you see is your first matrix multiplication between 2 vectors. So let's try that at some concrete example. Suppose we have the vectors 1, 2, 3 and 1, 0, 1. What you get as a result from this vector, not vector multiplication, but matrix multiplication, is 1 times 1 plus 2 times 0 plus 3 times 1, which gives us 3. So as a result, we get a 4. And you can also see that this is perfectly valid when it comes to the dimensions, because we have, in this case, 1 row, 3 columns. In this case, we have 3 rows and 1 column. Therefore, what we have here is an R1 cross 3 object multiplied by an R3 cross 1 object, these numbers go away and we are left with a R1 cross 1 object, which is exactly a scalar, right? So we actually have a matrix with one entry. So you could also put some brackets around, but you can leave them away. They don't matter if you look at scalars. But you could, of course, interpret this also as a 1 cross 1 matrix, which I also pointed out in my last video on matrices. Alright, so this is our first matrix multiplication that we did. This was a 4. And so let's look at some harder example where we can apply what we've learned right now. So suppose we have the matrices 1, 1, 2, and we have another matrix, in this case a bigger matrix, which would be 0, 1, 2, 3, 1, 1. Now, how do we multiply such two matrices? Because as you can see, we now have a bigger object as our standing vector, right? So how do we do that? And it's actually pretty easy. All you do from now on is you look for the rows or the row vectors, the lying vectors, basically these vectors in your first matrix, and you look for the columns or the standing vectors, so basically these vectors, in your second matrix. So in this case we would have one row vector and two column vectors. And to see what dimension our resulting matrix is gonna have, we can do again first a dimensional analysis. So we would have 1 row, 3 columns, 3 rows, 2 columns. So we would have an R1 cross 3 objects times, no dot, R3 cross 2 objects. The 3 goes away. We are left with an R1 cross 2 object, which would look like this. So it has 1 row and 2 columns. So we need 2 entries. 1, 2. That's exactly what we want because we have 2 scalar products, right? Or 2 matrix multiplications between a lying and a standing vector. So we get our first number, which would be this number here. We get from this first vector, lying vector, and this first standing vector. And we get our second entry from the second standing vector, so this one, together again with the first lying vector. So this is going to give us this second entry. Now let's calculate what we get. So we take basically the scalar product of this yellow vector with this yellow vector, and we would have 1 times 0, so 0, plus 1 times 2 gives us 2, plus 2 times 1 gives again 2, so we have 2 plus 2 gives us 4 for this first number. And for the second number in the matrix we would have 1 times 1 gives us 1, plus 1 times 3 plus 2. So we have a 6, which should be standing here. So we have already our first example of a more complicated matrix. Now let's look at an even more complicated example. Suppose we have the matrix 2, 1, 3, 0 times the matrix 1, 1, 3, 4. Then, if you multiply 2 square matrices together, what you get back is again a square matrix, namely of the same dimension. So in this case we would have an R2 cross 2 matrix times an R2 cross 2 matrix, you would get again an R2 cross 2 matrix, as you can see, because we can cross out these inner dimensions. We are left with the outer numbers. We get a 2 cross 2 matrix which has this form. And now again we need the numbers, and as you can see in this case, in comparison to up here, the only difference is that now we have 2 lying vectors here and again 2 standing vectors in the second matrix. So now we basically don't have 2 scalar products to get 2 numbers, but we have 4 scalar products to get 4 numbers. Exactly what we want. So let's try. The first row of the first matrix together with the first column of the second matrix gives us the first row and first column entry of this resulting matrix. Then the first row gives us again an entry in the first row, together with the second column of the second matrix gives us this entry. And then we have now, in comparison to up here, another row at the resulting matrix. So we take this second row vector in the first matrix together with this first row vector first column vector in the second matrix. We get this entry, and you obviously see that again from this vector together with this vector we will get this entry. So let's calculate, and we will see that for the blue entry we have 2 times 1 plus 1 times 3 gives us 5. Then for the red number, 2 times 1 plus 1 times 4 gives us 6. And then for the green we have 3 times 1 plus 0, we get 3. And then we have 3 times 1 plus 0 again gives us 3 again. Very nice. So as you can see, you always look at the first row vector of your first matrix, and this will give you the first row again in your resulting matrix, and each of these column vectors gives you an entry in this first row. And then you look at your second row, will give you again this second row. I hope you understand. Let's do the example up here. So now you know that you first look at this first row. We will get the first row in this resulting matrix, and you get the first entry by taking the scalar product of this first row vector together with this first standing vector or column vector of the second matrix. So you get a 1 times 1 plus 2 times 2 plus 3 times 0, which gives us a 5 up here. And you get the second entry by now looking at the scalar product between again this first row vector together with the second column vector. So you get a 1 plus 2 plus 6, which gives us 9 up here. So the first row always of a resulting matrix you get by looking at the first row of your first matrix, and you get the entries of this first row by multiplying or doing the scalar product of this first row together with all the different column vectors of the second matrix. So let's finish this by looking at this entry here, which would be Now the second row, so 0 times 1 plus 1 times 2 plus nothing, so we have a 2 standing here. Then again 0 times 1 plus 1 times 1 plus 0 times 2 gives us again a 1. And then we have 1 plus 4 plus nothing gives us 5. And we have for the last entry 1 plus 2 plus 4 gives us a 7. Perfect. So you can see that it is really not hard, and all you actually have to know to do matrix multiplication is the scalar product or the dot product. Now the last example is going to be the probably most used example, so your most important matrix multiplication in linear algebra, which is if you have a matrix and you multiply the matrix by a vector. So for example, we have 5, 3, 1, 2 as the matrix. So this is a 2 cross 2 matrix multiplied by the vector 1, 2. So this would be the vector, the standing vector is also a matrix, and it is an R2 cross 1 matrix. So what we get as the resulting matrix would be, we get rid of these numbers in between, an R2 cross 1 object as well. So the same object as this one, which is a standing vector. So we get some vectors, and all that's left to figure out is the entries of the vector. And now I hope you know how you would do that. We look first. Let's try white. So you look at this first row vector. This is going to give us the first row of the vector. So obviously this first entry. Together, if you take the scalar product of this row vector together with this standing vector. So we have a 5 plus a 6 gives us a nice 11 up here. And then we do the same for the second row, which gives us then the second entry in the vector. So we have a 1, 2 together again with 1, 2. Very creative. So this gives us a 1 plus 4 gives us a 5. And we are done. So I hope that you have now a good intuitive understanding of matrix multiplication and don't just do it as Wikipedia says it. Thanks for watching. Rate the video, subscribe, and see you soon again on LuckyMath.